Hi students, today in this lecture we discussing the topic is Cauchy's residue theorem. So in the previous lecture we discussed the topic is residue of analytic function. Okay, so in this theorem to finding integration of the given complex variable function. So how to finding the complex variable function? Already we using that formula Cauchy's integral formula, Cauchy's theorem, also using to finding complex variable integration, and this is also another theorem to finding the complex variable integration. So how to finding by using residues, using the residues of the given function at its fold, and first to finding the folds of the given function and next to finding residue at that folds, then using that one to finding integration of complex variable function. Okay na? Okay, first of all we see that statement of this theorem. Yeah, the statement is if f of z is analytic inside and on a simple closed curve C, except at a finite number of folds z1, z2, up to so on zn inside C, and r1, r2, up to so on rn are the residues of these points respectively, then integration of f of z over the region C dz is equal to 2 pi I into r1 plus r2 plus up to so on rn, and this is the finding the integration of the given function f of z over the region C, which is equal to formula 2 pi I. 2 pi I is a fixed. Next into the sum of the residues r1. r1 is the residue of the given function f of z at the first pole z1. Similarly r2. r2 is the residue of f of z at z2. Similarly up to so on rn is the residue of f of z at zn. And what are the z1, z2 up to so on zn? The folds of the given function. But the folds means the given function is not analytic at that points, and z1, z2 up to so on zn all are inside, and inside low at the point the function is not analytic. Okay na? And only not at the point fold as compulsory inside diagonal. In case outside is not required, is outside is a not we cannot discussing about that outside points. Only inside of the region you have to finding the residues. There is any points, 1 point or 2 points or any point depend on the given function. So this is the Cauchy's residue theorem, where the integral is taken in the anti-clockwise direction around C, and using now integration along the only anti-clockwise direction, that is a positive direction. So this is a statement of Cauchy's residue theorem. Okay, now we see the example on this theorem. Yeah, first example, use Cauchy's residue theorem, evaluate integration over C 2 into e power z by z plus 1 whole cube into dz with the given region mod z minus 1 is equal to 3. So mod z minus 1 is equal to 3 means the center is the 1, 0 and radius is 3. Okay na? See the solution. Let the function f of z is equal to 2 into e power z by z plus 1 whole cube. Okay, clearly for finding the folds, how to finding the folds? The denominator is must to be equal to 0. for poles of f of z. The denominator is z plus 1 whole cube is equal to 0. So that implies z is equal to minus 1. Z is equal to minus 1 is pole of order 3. And minus 1 is the pole is repeated 3 times. So that is order 3. And the reason is mod z minus 1 is equal to 3. That implies the center is 1 comma 0, radius 3. Okay na? So in this region, now we will discussing the point pole. The pole is inside or outside. Now verifying. So radius 3 kada, and the point is minus 1. Minus 1 is around the must be inside of the region. Left side radius and the minus 3, right side 3 kada, and the minus 1 is in the region. Okay. So only single point pole. Now finding the residue at minus 1 using that formula for finding the residue formula. So clearly the point z is equal to minus 1 is inside of C. So residue of f of z at pole z is equal to minus 1. Like already I told in the previous class, in the previous lecture, I told the formula, residue formula at z is equal to a of order m. And m is equal to 3 and 3 times repeated here, the pole is so this is the R1. And R1 means at the only first point, single point Z1. Z1 is equal to minus 1. At the point that 1, residue is R1. That is the residue of f of z at z is equal to minus 1. That is equal to formula 1 by m minus 1 factorial. M is equal to order 3 kada. Avuna? Minus 1 is repeated 3 times. That is m is equal to 3 and 3 minus 1 factorial. Limit z tends to minus 1. D power 3 minus 1 by dz power 3 minus 1. D power m minus 1 kada by dz power m minus 1, the formula. Next z plus 1 whole cube and z minus a power m into f of z. So f of z substituting the given function. Okay. That is equal to 1 by 2 factorial limit z tends to minus 1 d square by dz square of z plus 1 whole cube into function f of z is equal to 2 into e power z by z plus 1 whole cube. So simplification here, z plus 1 whole cube is a cancel. 1 by 2 into limit z tends to minus 1. So differentiating. So that is equal to differentiating 2 is a constant. Okay. Derivative of e power z 2 times. 2 times derivative is the e power z derivative e power z. Again derivative of e power z e power z. So that is 2 into e power z. Now simplification is z is equal substituting minus 1. Okay na? Continue. So that is equal to e power minus 1. 2 cancel here. Z is equal minus 1 to e power minus 1. This is the residue at z is equal to minus 1 of the given function. So this residue substituting in the theorem, Cauchy's residue theorem. So by Cauchy's residue theorem, this is the Cauchy's residue theorem and okay na. So 2 pi I into R1 plus R2, but only in this problem only one residue. So R2 up to some R is not required. Okay na. That is equal to, therefore given function integration over C f of z is equal to here 2 into e power z by z plus 1 whole cube into dz is equal to 2 pi I into only R1. That is equal to R1 is equal to e power minus 1. Therefore 2 pi I into e power minus 1 is the required value of the given integral function. Okay na. So this is the Cauchy's residue theorem. Okay. Okay. See the next example. Use Cauchy's residue theorem. Evaluate integration over C 2z minus 1 by z into z plus 2 into 2z plus 1 dz, where the region is mod z is equal to 1 and center is 0 comma 0, radius is 1. See the solution. Let f of z is equal to given function 2z minus 1 by z into z plus 2 into 2z plus 1. So clearly for finding the poles, function of f of z, the denominator is 0. the denominator is z into z plus 2 into z 2z plus 1 is equal 0 for finding folds. Okay, now what are the folds here? Z is equal 0 is a clearly the simple fold because only one time repeated. 0 is the pole of order 1, simple fold. Next to z is equal to minus 2. So z is equal to minus 2 is also fold of order 1 and this is also simple fold. Next to 2z plus 1 is equal to 0 and z is equal minus 1 by 2, which is also simple fold, is also order 1. We are getting 3 folds. No? So 3 folds are inside or outside. Now verifying. Okay, now. And the given region C is mod z is equal to 1. That is x square plus y square is equal to 1. You can see the graph. This is a circle given region x square plus y square is equal to 1. Radius is 1. 1 minus 1, 1. Okay, na? So see the points here, z is equal to 0 and origin. So this z is equal to 0. Next to z is equal to minus 2. So minus 2 and okay. Next to z is equal to minus 1 by 2. So z is equal to minus 1 is the point on x-axis only. So 0 is the inside of this circle. Next to minus 1 by 2 is also inside of the circle. Next to minus 2 is the outside. So minus 2 is not required. We will not discuss it. Now finding the residues on at the points 0 and minus 1 by 2. Only 2 points we have to finding the residues. So that is equal, z is equal 0 is inside of C. Z is equal minus 1 by 2 is the inside of C. Z is equal to minus 2 is outside of C. Only 2 points inside. So now to find residues at 0 and minus 1 by 2 only. Okay. Now we will continue now finding the residues. Okay, residue of f of z at pole z is equal to 0 using that formula, residue formula. So this is a residue formula. R1 at the first point z1 is equal to 0 kada. Residue of f of z at z is equal to 0. Limit z tends to 0, z minus 0 into f of z. So f of z substituting here. Limit z tends to 0, z f of z function is. No? So that is equal simplification. Z is a cancel here. Z is equal to 0 substituting 0 minus 1 by 0 plus 2 into 0 plus 1. That is equal to minus 1 by 2 is the first residue at z is equal to 0. Similarly, we have to finding the second residue at z is equal to minus 1 by 2. That is equal to, at the residue at pole z is equal to minus 1 by 2. So same formula at the point z is equal to minus 2 R2. No? Limit z tends to minus 1 by 2 z plus a kada. Ante z plus 1 by 2 into f of z. Limit z tends to minus 1 by 2 z plus 1 by 2 into f of z function substituting here. So that is equal to a simplification, take the LCM 2z plus 1 by 2. Here 2z plus 1, here 2z plus 1 cancel. Remaining z is equal minus 1 by 2 substituting. That is equal 1 by 2 into minus 1 by 2 minus 1. Ikkada z minus 1 by 2 into minus 1 by 2 plus 2. So this is a simplification 4 by 3. It is second residue. So by Cauchy's residue theorem, this is the formula. Here only 2 residues here. Ante 2 pi I into R1 plus R2 only. Okay. So given function is a given integral. So this is a given integral 2 pi I into R1 plus R2 only. So 2 pi I into R1 is equal minus 1 by 2 plus R2 is equal to 4 by 3. The simplification is 5 by 3 into pi I. This is the required value of given integral. Okay. This is understood. Example. Okay. Yeah. See the another example. Use Cauchy's residue theorem. Evaluate integration over C 1 by z square plus 1 into z square minus 4 into dz. where the region mod z is equal to 1.5. And the center is 0, 0, radius is 1.5. So solution, let the f of z is equal given function. Now finding the poles of the given function, assumption denominator is equal to 0. So z square plus 1 into z square minus 4 is equal to 0. So z is equal to plus or minus I, z is equal to plus or minus 2. Children, I minus I, 2 minus 2. So these are all simple folds, and all 4 points are differentiated and one time repeated. So all are simple folds. So given region mod z is equal 1.5, that is equal x square plus y square 1.5 whole square. The radius is 1.5. So now verifying this all points are inside or outside. Yeah, see the graph. So this is a circle. Okay, this is a circle. Radius 1.5 whole square. So radius 1.5. Children, radius 1.5, 1.5, 1.5. So points here. First point I and we choosing imaginary on y-axis. Ikkada idi I and. Okay. Next to minus I. Minus I is also on imaginary y-axis. So this is a minus I. Okay. Next to 2. 2 is a real number on x-axis. Ikkada chudandi. Ikkada 2. Okay. Next to minus 2. And the minus 2 and ikkada minus 2. So observe cheyandi akkada. Only inside are 2 points, I minus I, and 2 minus 2 are both are outside. So it's not required 2 and minus 2. Now finding residues at the point I and minus I. R1, R2 finding. At Z1 is equal to I, Z2 is equal to minus I. So clearly Z is equal to I is the inside of C, Z is equal to minus I is the inside of C. Z is equal to is outside of C, Z is equal to minus 2 is outside of C. So now to find the residues at I and minus I only 2 residues. Okay, I'll continue. The first one, residue of f of z at pole z is equal to I. So R1 is equal to formula residue of f of z at z is equal to I, limit z tends to I, z minus I into f of z. So f of z is equal, substituting here, this is f of z. So z is equal to I. So z minus I ga, take the factorization. Z square plus 1 means z minus I into z plus I ga. So one z minus I is cancel అయిపోతుంది చూడండి. ఓకేనా, ఇక్కడ చూడండి z square plus 1 can be write z plus I into z minus I. So z minus I, z minus is a cancel. Now z is equal to I, replacing here, that is equal to 1 by I plus I square minus 4. The simplification minus 1 by 10I. This is first residue at z is equal to I. The second pole at z is equal to minus I. Now finding R2. Residue of f of z at pole z is equal to minus I. So R2 is equal to residue of f of z at z minus I. Z is equal to minus I. That is equal to limit z tends to minus I, z plus I into f of z. Substituting f of z function here. Okay na? And z square plus 1 also can be at the separating factorization. Z plus I into z minus I. One z plus I is a cancel. Na? Z plus I, z plus I cancel. Remaining 1 by z minus I into z square minus 4. So substituting z is equal to minus I here. So 1 by minus I. So z square means minus I square minus 4. That is equal to here minus I square అంటే minus 1 కదా అవునా, minus 1 whole square అంటే 1, I square అంటే minus 1 minus 4 minus 5 into minus 2I, so plus 10I. So this is R2, second residue. Therefore now using the by Cauchy's residue theorem, this is a Cauchy's residue theorem, only up to choosing R1 plus R2. This is the given integral 2 pi I into R1 plus R2. So 2 pi I into R1 is equal to minus 1 by 10I plus 1 by 10I. So simplification is 0. This is the required value of the given integral. Okay, is understood? Yeah, okay. Yeah. Okay, for more videos, please do subscribe my channel and like, share it. Thank you.